Good afternoon or good morning, folks. How are you? And welcome back to Takeo Tuesday. John Barba here from Takeo Comfort Solutions, ready to spend a fun and crazy hour with you talking about what's new in hydronics and our topic of the day, which is flow, head, and sizing for ECM circulators. So welcome, everybody. Thank you very much for being with us. We do appreciate the gift of your time today, and hopefully this will be a fun session for you. A couple things. First and foremost, as always, when we do one of these sessions, we find that it's best if you treat it as you would treat a live classroom session, meaning I know we're online and everything. If it's very tempting to check email, Facebook, blah, 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 blah. I get it. Try to resist that for the next hour. Focus on what we're doing here. And the best way for you to do that, we have found, is with a pad and a pen, piece of paper, or a pad and a pen, a pad of paper and a pen. There we go. I know I could get it out. A pad of paper and a pen right in front of you, and take notes like you would if you were in a classroom. That keeps you engaged and keeps you from wandering and clicking and doing things like that. That's just a great way to make the most out of a webinar. You will be getting an email tomorrow with a link to the recording of this session, so you can view it as many times as you want. So don't worry if you miss anything. But please feel free to make sure you do all of that, and you have your you have your notes with you, so that'll help you get the most out of it. Also, please look on your control panel for your comment question/chat section. That's going to be how you ask questions during this presentation. And please feel free to ask any question you want at any time during the session. We don't wait until the very end of the session to do a question and answer section. We try to answer them as they come along. And greetings to Rick Mayo. How are you, Rick, from Takeo Comfort Solutions? All righty. We did finally get logged in, huh? I guess new computer takes about 8 or 9 chimes to kind of log in. It's kind of interesting, huh?
Not right.
It's crazy. It is crazy. But welcome, Rick. Rick is out in Mesquite, Nevada. So it's 9 o'clock in the morning where you are, and you're having your coffee. Excellent. Very good. Very good. But for all of you folks out there, if you could go to that chat section for me and just type in a little bit of a hi, hello, how are you? So I know you can hear me and that you're engaged. And also, if you could do that for us, just let us know where you're from so we can hear. So we got a little bit of a roll call, which is always fun to see where everybody's from. So we got some highs and some hellos from some folks out there. But yeah, if you could all do that for me, that would be terrific. We got a hello from Nebraska, Chicago. Very good. Very good. Let's see, Robert, do you have a certificate of completion? Yes, of course. We in that email you will get tomorrow, Robert. It will include a link to the recording, as well as a link to download a certificate of attendance. So terrific. Minnesota, Alabama, Georgia, Kansas City, Colorado, Missouri, Michigan, Rhode Island, Alabama, again, Lawrenceville, Pennsylvania, Phoenix, Quebec. Oh, this is terrific. Rick, we have a nationwide and multinational group here, so this is really cool.
We love it.
We love it. We love it. Okay, terrific, terrific. And Stephen Rogers says a special hello to Rick's facial hair, which actually usually arrives in a room a good 3 minutes before Rick does. That's his hair, man. That's excellent. Very good. So anyway, so good. As we go through, please type in your questions and we'll do our very best to answer them as best we can. If we don't know the answer, we'll tell you that too, because hey, I have yet to meet the guy who knows everything there is to know about hydronics. Okay, I've met a few people who think they're that guy, but trust me, they're not. Okay, so let's get started. One of my favorite topics today is really understanding what residential ECM circulators do, and most importantly, what they don't do. They're not magic, okay? We talk about sizing, and I've had this question come up many times in class when we talk about figuring flow and head when you're using a variable speed circulator. And sometimes people look at me and says, why do we worry about that? It's variable speed, man. It'll just figure it out and change and adapt, right? No, they don't do it that way, because it's just not the way it goes, right? It's not the way it goes. As Neil Young said in Rust Never Sleeps, there's more to a picture than meets the eye. Hey, hey, my. There's a lot more going on here, okay, than just, oh, variable speed, it takes care of everything. We don't have to worry about it. The reason we do have to worry about finding flow and figuring out head and understanding the interplay between that requirement and what circulators can do is because These things are programmable, right? We can set it up in constant pressure. We can set it up in proportional pressure. There's even an automatic mode, but that doesn't do what you think it does. It doesn't size itself. And then we have the whole delta T scenario that we have to look into as well. A delta T variable speed pump gets closer to what we're talking about than anything else. So we'll take a good look at that as well. But no matter what, with any circulator, fixed speed, multi-speed, variable speed, delta P, delta T, these four things are always at play: flow, head, performance curves, or control curves, if you will, and system curves. Once we understand those four basic things, circulator selection starts to become very simple. Understanding how we select these circulators and what impact the circulator we choose has on overall system performance, as we shall see. So flow, head, performance curves, and system curves. Let's talk about flow and head real quickly, because that's the foundation. Circulators deliver gallons per minute flow rate. As those gallons per minute are flowing through pipe, okay, that pipe imparts friction loss on the piping. That's known as head loss or friction loss. And our circulator has to be able to overcome that friction loss in order to deliver the flow rate required in order to satisfy the BTU load at a given point in time. So it's all interconnected, all right? We cannot separate flow and head. As flow goes up in a system, the head goes up exponentially, a lot. The head goes up a lot. What's that word, Rick? Can you say that word for me?
Exponentially.
Exponentially, thank you. There we go. As flow goes up, head goes up exponentially. It's a function of the square of the increase. So we'll show you how to figure it out the right way in just a moment. But first, let's just take a look at the universal hydronics formula. This thing is fundamental to what we do. It's as important to professionals in the hydronics industry as torts are to a lawyer or as anatomy is to a doctor. It's fundamental to what we do. And the universal hydronics formula states that GPM is equal to BTUH divided by the product of delta T times 500. So technically, you're going to want to see parentheses right there. The product of delta T times 500. Now, GPM stands for gallons per minute. That's the flow rate we need to deliver the BTUs required. BTUH, of course, is the BTUs required. Now, the BTUH we know is going to change every day, right? It's going to change based on how many zones are open and closed at a given point in time, if it is in fact a zone valve job. And it's going to vary based on how cold it is outside. We typically do our design for that quote unquote coldest day of the year design conditions. So that's our BTUH. That's the heating load, and the heat loss will tell you that. Delta T is our designed for temperature drop of the fluid as it goes through the system. Typically, we design residential hydronics to a delta T of 20 degrees, meaning, let's say we're talking about a cast iron boiler. The water goes out at 180, it comes back at 160. That's what we're designing for. Now, it doesn't always happen. In fact, it rarely happens in real life, but that's what we're designing for. So it goes out at 180, comes back at 160. That's an average water temperature of 170 for sizing our radiation. Lower temperature boilers, modulating condensing boilers, may be under design conditions. We design to 140 going out, 120 coming back for an average of 130. So there's your 20-degree delta T. Residential radiant might often get designed to a 10-degree delta T simply for consistent floor surface temperatures. Maybe in a concrete slab, a 4-inch concrete slab, you don't need to, but those lower mass systems or between the floor joist types of installations, yeah, you generally design to a delta T of 10 to keep the floor surface temperatures consistent. And then 500 is a mathematical constant. It's a rule of thumb, if you will, if we're using 100% water, all right? 500 is basically comes from multiplying the weight of 1 gallon of water, 8.33 pounds per gallon, times the number of minutes in an hour, 60, times the specific gravity of the fluid. Water has a specific gravity of 1, times the specific heat of the fluid. Water has a specific heat of 1, 8.33 times 60 times 1 times 1. That's 499.8. We'll call that 500. Now, Rick, glycol is going to change that number, right? The more glycol you put in, what's going to happen to that 500 number?
That number is going to go down, and that's somewhat counterintuitive. But the lower the number is, the resultant calculation will actually slightly increase the flow to compensate.
Right, the things that are going to change that number would be the weight of 1 gallon of glycol, whatever the glycol to water mix is. That's going to change the weight, but the specific gravity and the specific heat specifically are going to change, pardon the pun, because they are both, glycol simply doesn't transfer heat as effectively as water does. So yeah, the more glycol you put in, the more flow you're going to need to deliver the same amount of BTUs. The more flow you have to deliver the same amount of BTUs, the more head loss you're going to have in the piping system. So glycol complicates things, and there's no real fixed number to use there. It just depends on what you're using. So that's where all those numbers come from. Practical application. Let's say I have a zone of something, doesn't matter what, a zone of something out there that totals 30,000 BTUs. So that's a big zone. 30,000 BTUs is a pretty big honking zone if you think about it. And I want to figure out what my flow rate is. So 30,000 divided by 20 times 500, or 10,000. 30,000 divided by 10,000, that gives me a required flow rate under design conditions of 3 gallons per minute. 3 gallons per minute. So that's what we need, and that's where we're talking about here in terms of flow. Now, based on that, we can now size our pipe. All right, we can now size our pipe, and we can figure out our head loss, or the head loss or the friction loss. So what is head loss? Well, it is friction loss. Water rubs against the sides of the pipe. That's going to cause friction loss. Water runs into fittings and has changes of direction. That's going to cause friction loss as well. Okay, so the circulator has to overcome that friction loss in order to deliver the flow rate that you need to get the BTUs required. One good way to think about friction loss and the role of circulators, I don't know if you remember this thing, if you were a kid and you played with Hot Wheels, which basically was my life from age 8 to age 11. Hot Wheels just dominated, and then I discovered girls, I guess so. But Hot Wheels were dominant in my life. And this was the thing, I never really got one because my parents wouldn't get me one. The supercharger. The supercharger was cool because up until the supercharger, Hot Wheels were a gravity thing. Okay, you had to go downhill and do the loop-de-loops and all that. What the supercharger allowed you to do would be to lay out a big old oval with your orange track. And the supercharger was this little hut that you see here, and it had these rubber wheels that were spinning, and the car would enter the supercharger, the rubber wheels would grab it and shoot it out the other side at a higher velocity. Think about it, that's what a circulator does. That's what a circulator does. But as the car goes through the orange track, okay, the Hot Wheels themselves, the cars themselves, think of them as the water, and think of the orange track as the pipe. As the car goes through that pipe, the friction that it encounters, whether it's rubbing up against the sides, making turns or whatever, that is causing that velocity to go down. Now, if we equate velocity to pressure in the system, we kind of get an idea of what we're talking about here. This is a darn good analogy, actually, in my idea. The supercharger itself is the circulator. And what it does is it's trying to overcome the friction loss of the orange track to make the car go all the way around the oval. And again, if you think of it like that, that's telling us what a circulator does. And friction, and understanding friction loss. Now, how to figure out friction loss? This is the easiest way. Well, there's easy ways. This is the most accurate way. That is also easy. Using chart or table number 6 from the Copper Tube Handbook that's published by the Copper Tube Development Association. If you look it up online, you can download the book. And what it does is it breaks down pressure loss of water due to friction in types K, L, and M copper tubing, but it's giving it to us in PSI per linear foot of pipe, right? PSI per linear foot of pipe. Now, and it also breaks it down based on flow, all right? Based on flow, specific flow rates. Now, our flow rate in this case was 3 gallons per minute. Now, our pipe sizing guidelines will tell us if we're at a flow rate of 3 gallons per minute, we're going to be looking at 3/4 inch type M copper tubing in, let's say, a fin tube zone. So if we follow 3 gallons a minute over to the 3/4 inch M line, we're going to see that our pressure loss in PSI for 1 foot of pipe is 0.009 PSI for 1 foot of pipe. Let's say that total length from the Gazzouta side of the circulator all the way through the system back to the Gazinda side of the circulator is 285 feet for that one loop of pipe, right? 285 feet. So 0.009 PSI per foot times 285 feet. The feet cancel each other out, and we're left with PSI. So 2.57 PSI. Now, how do we convert PSI into feet ahead? We're going to multiply it by 2.31 because 1 PSI worth of pressure loss is equal to 2.31 feet of head loss. So if we multiply that out, 2.57 times 2.31 feet ahead per foot of pipe, we will get 2.31 feet ahead per PSI. We will get 5.9 feet of head. We'll call it 6. So this particular zone will require a circulator that can give us 3 gallons per minute while overcoming 6 feet of head. If you think about it, that's not a lot of head. 3 gallons a minute, 6 feet. That's a 30,000 BTU zone that's 285 feet long, taking the fittings into account, okay, the equivalent length of pipe for each fitting, 285 feet. That's not a lot of head, all right? So we don't need a big circulator here to make this work, all right? So that's our flow and our head requirement, okay, our flow and our head requirement. Now we want to understand system curves and pump curves. I want to just check, make sure, Rick, do we have any questions that have come in?
The only one was, I think Fletcher wanted to know why they couldn't see other people's questions and responses and stuff.
Yeah, the system does not allow for that, Fletcher, but we will be, as the questions come in, we'll be answering them. We'll be reading them off and answering them. So you won't be able to see them, but you will be able to hear them. So there we go. Is that right? Now let's talk about system curves and pump curves, and we'll see how flow and head interact. Pump performance curve, or a control curve, or a performance curve, however we want to define it, is what we come up with when we develop our circulators. It's the performance that this circulator will do. All right. So what we show here is an example of a pump curve. All right, right here, an example of a pump curve. And the way we do this is we have a circulator and in a system, and we have a flow control valve and a pressure meter, pressure gauge. So the first thing we do is we close that flow valve altogether, so there's no flow, and then we turn on the pump. So that would be 0 gallons per minute right here, 0 GPM, and we read the no flow pressure, which should be the highest that circulator could do. We read it in PSI, we multiply it by 2.31, and that gives us the shut-off head, if you will. Then we go to 1 gallon a minute, 2 gallons a minute, 3, 4, 5, 6, and so on, and we read the pressure, can multiply it by 2.31, and we plot it on this chart, okay, on this graph. And then once we have all those plots, we draw the line, connect the dots. There's our performance curve. In a standard efficiency circulator, you'll see a curve that looks like this. It kind of goes down and to the right. As flow goes up, the circulator's ability to overcome friction loss goes down. That's just the way it is. That's why it's called a curve. Now, in constant pressure ECM systems, you'll see actually a flat curve pump, an absolutely flat curve pump. We're able to maintain, let's say, 5 foot ahead constant pressure or 10 foot ahead constant pressure simply by varying the speed of the impeller. In a single speed circulator, AC circulator, it's just 1 speed. So you want it to do more flow, it's going to give you less pressure differential, going to create, overcome less head loss. It's just the way it works. So there's the pump curve. The system curve gets interesting. Now the system curve is like a unique hydraulic fingerprint for each piping system. Every piping system out there has a really unique fingerprint that separates it from everything else. And the reason it's important, let me go back a step. If you remember doing charts and graphs in like 5th or 6th grade math and thinking, boy, this is stupid. I'm never going to use this in the real world. No one's ever going to ask me to do a bunch of math and plot these things out on a graph and make me connect the dots. This is ridiculous. Today's the day we're going to do this. Okay, today's the day it becomes part of your life again. The system curve, there's a mathematical relationship between flow and head. Again, as flow goes up, head goes up, let me try it again, exponentially. What the system curve represents is just a diagram of that relationship, okay? The reason it's important is this right here, what we call the duty point, or where the system's actually gonna operate. So let's explain this. System goes up, as we said, head goes up exponentially. When you do the math, and I'm gonna show you the math You're never gonna, I don't know as you'll ever do the math, but just know where it comes from. Once we figure out the system curve and plot it on that curve, on that graph, along with the pump curve, the point where the two intersect is where the system will work. So let's say I needed, let's say this is 4 gallons a minute at, let's say 5 feet ahead. I'm just throwing some numbers out there, 5 feet ahead, 4 GPM at 5 feet ahead. This is what I need. I plop that circulator on that system. I'm never going to ever see 4 gallons a minute at 5 foot ahead. What I'm going to see is this, and let's call that 8 gallons a minute at, let's call it 13 feet ahead. That's where that zone is always going to work. Every time that circulator comes on, I'm going to be pumping at a rate of 8 gallons per minute at 13 feet ahead, every single time. Now, 4 gallons a minute, let's say that's 40,000 BTUs, right? Under design condition, that zone requires 40,000 BTUs. Well, if I'm pumping 8 gallons a minute, that doesn't mean I'm giving it 80,000 BTUs, and that should be enough. What it means is I've got twice as much flow as I need to deliver those 40,000 BTUs. So the thing that's going to have to give here, if I go, you know, if I write this out on mathematically, okay, 8 gallons per minute equals 40,000 BTUs divided by my delta T times 500. 500 is going to stay the same. My design for delta T was 20. I'm never going to see 20. In fact, the best that delta T is ever going to be in this example is 10. And as it gets warmer out, that delta T is going to shrink, because as it gets warmer out, this goes down. So let's say it's 20,000 BTUs. It's warmer out. It's 50% load. I'm not going to have a 10-degree delta T. I'm going to have a 5-degree delta T. And folks out there in webinar land, type it in. If I have a 5-degree delta T, what's going to happen with my boiler? And what's going to happen with all the moving parts? Tell me what you think. All right? Tell me what you think. Because I'd like to hear what, if you know, what's going to happen if I work with at best a 10-degree delta T and more than half of the heating season, something less than 5. Yeah, short cycling,
Yeah,
absolutely. Boilers are
you
going
got
to
it covered.
short cycle like crazy. And Rick, is a short cycling boiler an efficient boiler?
No, that's an easy one, John. You threw
That's
me a
an easy one.
real easy
Absolutely.
one.
It's
You want
not
me to expound, or you just want me to answer the question?
no, you may expound. You may expound.
No, no, it's not efficient. It's going to, well, let's take them back to that old saying we used to use about efficiency. And of course, I shouldn't have said that, because now I can't think of the term, but I'll come up with it and I'll shoot back in. Overall system efficiency, we used to call it steady state efficiency. So steady state efficiency is the highest efficiency we can obtain running under a steady condition. The more we chop up that steady condition, the more that efficiency starts to drop. So no, when you cycle a piece of equipment, and the more you cycle it, the less overall efficiency you have. You don't have that good steady state efficiency that we used to use quite a bit. So anyway, I'm dealing with a cold or a flu too, so my apologies for my voice and my lack of brain matter right now. So
Yeah, you just sound a little congested, but hey, as long as it's not COVID and just a cold, you're good, man. That's all right. Now, how do we plot this system curve? Like I told you, there's a math formula, and I'm going to inflict it upon you real quickly, but I'm going to show you an easier way to do it. Here's the math formula. Head 1 divided by head 2 equals flow 1 divided by flow 2 squared. Simple, right? What the heck is all this? Well, understand, we know flow 1 and we know head 1, right? In an example, the one we just did, we had 3 gallons a minute at 5 feet ahead was our example, okay? The way we would use this formula is we can plug whatever number we want to into flow 2. So we want to find out what the head is going to be at 2 gallons a minute. I can do that. I can, 4 gallons a minute, 6 gallons, whatever it is. And I would do a bunch of different numbers. So I have a bunch of different, coordinates to put on that graph. Let's show you how this would work in the real world. So again, 3 gallons, let's say the example we used earlier was 3 gallons a minute at 6 feet ahead. Okay, when we design our first. So is the flow. And now I want to find out what the head would be if I doubled the flow to 6 gallons a minute. So
John,
head flow 1 is 3, head 1 is 6 feet ahead. Yep.
turn your video camera
Are you
off.
there,
If
Rick? I can hear you.
yeah, turn your video camera off. Well, I think we're losing some bandwidth or something. Your voice is, we're
Okay,
losing your voice.
very good.
Okay.
Okay, there we go. Well, the camera's off. So I have 3 gallons a minute at 6 feet ahead. I want to find out what the head will be at 6 gallons a minute, which is right here. So that's flow 2. Head 2 is x. And now it's simple algebra. I try to solve for x. So 6 divided by x equals, well, 3 divided by 6 is 0.5 squared, and I want to square that. So 6 divided by x is going to equal 0.5 times 0.5, which is 0.25. Now I want to solve for x. So what I'm going to do is try to isolate x. Now I multiply both sides by x. So 6 equals 0.25x. Now to solve for x, I'm going to divide both sides by 0.25. X equals 24. So head 2 in this case is 24 feet. So at 3 GPM, I'm at 6 feet ahead. At 6 GPM, I'm at 24 feet ahead. So you can see it goes up exponentially, a function of the square of the increase. So it's not a straight line, it's not linear, it's kind of, again, as we said, exponential. Now you would do this math calculation for a whole bunch of different flow rates. Kudos to Bell and Gossett for coming up with the system sizer wheel. Gil Carlson back in the 60s developed this as a shortcut for some of his own calculations. They figured out what it was, and then they kind of mass produced it. And I have a copy of the original sitting about 6 feet to my left here, of the original hand-drawn one. What scale 5 allows you to do is figure out the different points on the plot without doing any math. What you do is you line up your GPM right here, 3 gallons a minute, with your feet ahead, 6, and then you just read up and down. Okay, 1 gallon a minute, that head loss looks like it's 0.7 through that piping system. At 2 gallons a minute, it looks like we're at, say, 2.75 feet ahead. 3 gallons a minute is at 6. 4 gallons a minute is 11. 5 gallons a minute looks like it is 17. 6 gallons a minute, there's your 24. All right, so all of those are there. You just follow along and you can figure out the different points on your graph. Then you go to a graph, you plop them into place, overlay the pump performance curve, and here's what you got. Okay, so if I were to use, let's say, the 0015 fixed speed circulator, 3-speed circulator, if I set it to high, I'd be working right about here. All right, I need 3 at 6, but if I set it to high, I'm almost at 5 at almost 15. If I go to medium speed, I'm going to be right here. So I'm at almost 4.5 gallons a minute. Again, over pumping here. At low speed would be my best choice. I'm at a little less than 3.5 gallons a minute. That would be the best selection for something like that. So you see how your choice of circulator, your choice of circulator is going to matter, because the system will work where the system curve intersects the pump curve. What does this all have to do with variable speed circulators? You may very well be asking. Well, a lot. And here's the thing, with ECM circulators, there is no such thing as magic. People think, oh, I put it in, it figures out everything for me. It's a nice idea, absolute nonsense, but it is a nice idea. There is no such thing as magic. We're still talking about system curves and pump performance curves, but in this case, we're talking about control curves, because we have a control that can set the curve to force that pump to act where we want it to act. But we have to understand what these different things do in order to get the most out of an ECM circulator. They do not size themselves, and there's an asterisk there because there is a little bit of a twist to that when we start talking about delta T variable speed circulators. But they don't size themselves. I don't care how many times you push the magic button. And we're going to discuss delta T and delta P in the upcoming, for the remainder of our session. Let's talk about delta P variable speed circulators. Delta P circulators will vary their speed in order to maintain a specific pressure differential within the system. A circulator left to its own devices is a pressure differential machine. All right. Now, when we talked about fixed speed circulators, like our 3-speed or single speed circulators, we talked about a declining line like we showed there. What we can do with variable speed circulators, ECM technology, and different control curves is we can change the shape of that curve to a degree. So we have constant pressure modes and proportional pressure modes. The way a delta P circulator works is, again, it's trying to maintain a specific pressure differential within the system. Well, how does it know when things change? Let's take a zone valve system as an example. In a zone valve system, let's say I'm trying to maintain a 10 foot of head constant pressure differential within that system. All right, that's what I'm trying to maintain. Now it's just system curves and pump curves again. Okay, and let's say I want, let's say I have a system where I want 7 gallons a minute at 5 foot ahead, but I've chosen a 10 foot ahead constant pressure line. That not necessarily mean I do have the option to choose a 5, but let's just say I chose a 10. This again is where I want to be, but because I've chosen the 10 foot of head constant pressure control curve, and that's the operating mode, it's not going to work down here. It's going to work right there. And there's your system curve. What's going to happen is it's actually operating on this curve. Inside that brain, the engineers, the really smart guys, they programmed in a boatload of individual pump performance curves. There's a bunch of them in there. All right. And we can jump from one to another in order just to maintain our constant pressure. So let's say we're in a zone valve system, all zones are calling. Yeah, you know, I wanted to be down here, but I chose this operating mode, so I'm going to be right there. Now, let's say a zone closes. What's going to happen is that impeller is spinning against a certain resistance. When a zone valve closes, all of a sudden that impeller is spinning against more resistance. All right, because I have one fewer hole for all that water to go through. So there's a little bit more system resistance. What's going to happen is I'm going to get a new system curve, all right, a new system curve, because I've closed the zone, so I've got a completely new system curve, and it's going to intersect that existing pump curve maybe up there. What's going to happen is I'm going to operate up here at a higher pressure differential than what I've programmed for. The control is going to say, huh, that's not supposed to happen. We actually have to drop down so I'm back at that 10 foot ahead constant pressure line. It's basically interpreting this all through amp draw, essentially. There's no sensors in these things to speak of, all right? So what's going to happen is I'm going to bop up here, and in about a nanosecond, it's going to bop back down there, and it's going to look like that. So now I have a new system curve, a new operating point, and I'm working on a new pump curve that's going a little bit slower than the one I was working on before. Another zone closes, same thing happens, okay? I'm gonna go work up here. We're gonna sense that increasing resistance. The circulator is gonna slow down, and now I'm working on that curve, and so on until I'm down to my smallest zone. And now I'm working here. So my variable speed range is between here and here, all right? And that could be, let's say, between 30 watts and 18 watts, if you will. So that's how it's varying its speed, all right? It's got nothing to do with how many BTUs you need. It has everything to do with where you set the curve and what it's got to do to maintain its 10 foot ahead constant pressure. Now, if I had done a little bit of math and I knew I was at 7 gallons a minute and 5 foot ahead, and I chose the 5 foot ahead constant pressure line, now my variable speed range would be between here and here, and that could be between 15 watts and, let's say, 7 watts. So now by understanding the programming and understanding where I need to be, I can cut my electrical consumption by a heck of a lot, by at least half, all right? And I'm operating more towards where I need to be, because again, if I need 7 at 5 and I'm really operating up here at 9, It's still more flow than I need. My delta T is going to shrink, and I still am going to have some short cycling under design conditions. All right, and as it gets warmer out, that short cycling is just going to get worse. I'm still going to have some short cycling if I program it down here. I'm still going to have short cycling as it gets warmer out, but it won't be nearly as severe. In this case, I won't be able to get around it, but it won't be nearly as severe. Let me know if that makes sense in terms of how this thing operates. Okay, let's see what we have. Again, just make sure that we understand that this is how a delta P circulator in constant pressure mode will work. Go ahead, Rick.
Matthew had a point that you were making earlier, though. He was just adding to the fact that you know, I was talking about overall system efficiency and steady state efficiency, but he's making a point to say that yes, but what about the cycling of each of the pieces of equipment like igniters and relays and fans and all that other stuff? And that's a good point, Matthew.
Absolutely, yeah. I mean, you start wearing out, you know, very expensive components prematurely. We especially see that in mod con boilers. Oh my gosh, you know, you get a blower motor or something wears out in, you know, 4 years or 3 years. All of a sudden, that has to be replaced, if not under warranty. And you know, all the money you saved with a more efficient boiler now goes right out the window simply because we short cycled it into an early grave. That's an excellent point. Excellent point. Is that right? And again, here's just a graphic illustration with the 007E, which is a 10-foot ahead constant pressure circulator. There's no, it's very closely emulates the performance of our standard efficiency 007, but it is variable speed and constant pressure. So again, here you see what would happen. It's the same basic photograph, but it shows a specific circulator here and what happens when zones close. Now, as a zone pump, similar but different. As a zone pump, a delta P pump's not going to vary its speed because there's nothing within a zone that's ever going to cause a pressure differential change within a system. So let's say I have a zone that requires 2 gallons a minute at 5 feet ahead. This is where I want it to work. Ain't going to work there. It's going to work where the system curve intersects the pump performance control curve in this case. So really what I'm giving it is 3 gallons a minute at 10 foot ahead. So that's 50% more flow than it needs. I'll have about a one third lower delta T. I'm designing to a 20. I'm going to have about a 13, 14 degree delta T at best in this example. The other benefit here, and that is what it is. The benefit here is I'm probably going to be working at about 25 watts instead of 80 to 85 watts with a 007. There's your benefit. Overall performance in terms of flow is still going to be probably about the same. I don't see it being a whole lot different, but I've used fewer watts. Now, 0015E3 is a 3 setting. We talked about the 5 foot ahead and 10 foot ahead constant pressure settings. All right, let's give it, I'm going to throw a different example at you. Okay, different example. 8 gallons a minute, zone valve job, 8 gallons a minute at 7 foot ahead. Now, where would you set that? All right, we're kind of in between, we're in this no man's land between low at 5 foot ahead and medium at 10 foot ahead. So where would you set? You'd have to set it at medium, right? You'd have to set it at medium. And if we were to draw out that system curve, all zones calling, again, I'm out here at 9 gallons a minute, and that's working at full speed, 44 watts, okay? Not horrible, but that's just the way it is, okay? If I were to start to close zones. Now remember, or forget closing zones at this point. 8 gallons a minute right here. I have 4 gallons a minute right here. That's 50% load. So instead of saying it's like 0 degrees outside and I need 80,000 BTUs for this system, it's 35 degrees outside and I only need 40,000 BTUs. At 4 gallons, that's 4 gallons a minute. At 4 gallons a minute, the head is a little over 2. This is what I need, but again, that is what I'm getting. I need 4, I'm getting 9. My delta T is going to be less than 10 at that point. All right, it's going to be in single digits, and as zones close, it's simply going to get smaller and smaller. Let me know if that makes sense to everybody. I just dropped my pen here. So let me know if that makes sense to everybody.
Got some questions, John, that we should probably cover up. One individual is bringing up a good point. You know, can I put a throttling valve in there to increase the head? And So that's one of the questions. The other one is they want to know what the input to the circulator is that causes it to change its speed. Well, that's, again, pressure changes. As zone valves close, the pressure increases. But I think what he wants to nail down is how is it done? And it's done in the initial mapping. We put these circulators on test bench, and we know what the motor is feeling and seeing, so to speak, at all kinds of different operating ranges. And all it's really doing is saying, okay, I'm going to adjust so that my amp draw and my wattage and everything that it saw while it was on the test bench predicted a certain amount of GPM, and in this case, feet of head. So hopefully that clears things up. What about balancing valves, John?
Well, you could put a balancing valve in there, but it's not going to, it's to what end in this case? The circulator's still going to do what the circulator's going to do. It's still, if I have a balancing valve in here to throttle down the flow, yeah, I'm going to throttle down, but the circulator still wants to maintain that 10 foot ahead constant pressure. It's still looking at that amp draw in this example, right? So I'm not sure a throttling valve is going to do much for you here, or any kind of a balancing valve with an ECM. That's the way I would look at it. It's simply going to want to try to work on its performance curve or its control curve, because that's what it's been programmed to do. It doesn't know it doesn't know anything other than the resistance it's feeling and what you've programmed it to do. These things are obedient, okay? We call these things smart pumps, and they're not that smart. They really aren't, but what they are is obedient. They do what you tell them to do, okay? They do what you tell them to do. And they don't ask many questions, okay? So they are very obedient. So I'm not sure a balancing valve is going to throttle the pump in a way that's going to be effective like it would be with, say, a fixed speed circulator. I think it's going to want to work on that curve, and there's not much we can do about it. Can the brain parameters be changed or adjusted beyond what is pre-programmed? No, and not in a residential circulator. No, not at all. Now, in self-sensing circulators, you may have some parameters there where you can do some adjusting, because there's some crazy stuff in there that is really involved and detailed. So yes, they can. But in small residential circulators, you've got the adjustments you have, or with let's say the 0015E3 are the three that you see here: low, medium, and high. And you pick the one that's most appropriate in a residential application. When we get into, say, our 0018E with Bluetooth technology, which is going to be the subject of a later presentation, you will see that we have a lot more adjustability there. We can change these programs, change the parameters. We have a lot more options in terms of programming that make it really easy. Now, how do you find out what the pre-programmed parameters are? And as far as these circulators are concerned, your options are all printed in our literature on what you can do. Good questions. Okay, let's continue. Proportional pressure is an operating mode available in many ECM circulators, including some of ours. And basically now what you have is a declining, let's go back here one more, a declining pump performance curve. So as flow goes down, the head pressure differential created by the circulator goes down as well, at a different proportion. This is a 3-to-2 proportion. Some of them are 2-to-1 proportions. 2-to-1 proportion meaning it would go from 12 foot ahead down to 6 foot ahead. This is more of a 3-to-2, so it's going from 6 to just about 4 foot ahead. And again, the same thing applies. So let's say I've got 8 gallons a minute at 7 foot ahead right here. Okay, this is my requirement. No matter what, I'm going to be working right about here again at 9 gallons a minute. All right, that's where the system's going to operate. And again, I have the same problem at 4 gallons a minute, 50% load. I want to be down here. I'm going to be operating up there. There's really no other way of dealing with that. Where we're going to be, again, with zone valves, we're going to be varying our speed like so with different system curves. So what you may find, depending upon the layup, this is why proportional pressure with zone valves, if it's a steeper proportion, tend to be problematic, because let's say my highest head zone, just for giggles and grins, let's say it's 2 gallons a minute at 7 feet ahead. Doesn't really apply here. But if I had a higher head zone that was up here somewhere in a different type of system and I picked medium, I might wind up with a bit of a problem. So this illustration doesn't show it very well, but in some cases, proportional pressure, when most zone valves are closed, you might not have enough head pressure differential to satisfy a zone under design conditions when it's really cold out. We see that with proportional pressure in many instances, especially radiant systems where it's just not the right operating mode. Proportional pressure works best in continuous circulation systems with thermostatic radiator valves when we're talking about circulators of this size. The operation will slide up and down that proportional curve, and we'll see that a little bit more when we talk about TACO's active adapt in just a moment. And delta T circulators are going to be very different. A delta T circulator will vary its speed in order to maintain your designed for delta T within the system as much as possible. Because remember our formula, GPM equals BTUH divided by delta T times 500, right? Well, we know 500 is a constant, okay? Even if I have glycol, whatever that number is going to be, that's going to be a constant, okay? And we know BTU is going to change. BTUH is going to change based upon how many zones are open and closed at a given point in time, but it's also going to change based on the weather, how cold it is outside. All right, we've already talked about that. 50% load, it's just going to have a lower requirement for BTUs. Now, wouldn't it be ideal if we varied the flow in lockstep with the BTUs needed, as opposed to simply maintaining a specific pressure differential? Because there's no delta P in here, there is a delta T. If we vary the speed, well, let's go take a step back. If the delta T is fixed, meaning we're trying to maintain a specific delta T within that system for as much of the heating season as we can. If that delta T is fixed, we know the BTUH is going to vary. If the delta T is fixed, the BTUH is going to vary, and the flow will therefore vary in lockstep with the BTUH. Okay? In a system, using a fixed speed circulator, if the GPM is fixed and the BTUH varies, then the delta T will have to vary, right? The delta T will have to vary. So if the GPM is fixed and the BTU changes, the delta T has to vary. If the delta T is fixed and the BTUH changes, the GPM has to vary. And that's the whole idea behind delta T pumping. So again, we go to our 8 gallons a minute, 7 foot ahead zone valve package here, right? And let's say it's a 3-zone system. A 3-zone system is going to have 7 different system curves, one system curve for every possible combination of zones that's calling at a given point in time. Let's count them out. Okay, you got zone 1 by itself, zone 2 by itself, zone 3 by itself, zone 1 and 2, zones 1 and 3, zones 2 and 3, and zones 1, 2, and 3. I think that's all of them. That's 7, right? What's going to happen here is, because I set this thing up with actual strap-on sensors, one on the supply, the hottest water going out, and one on the common return, the blend of all of the return water temperatures. And I want to maintain, let's say, a 20-degree delta T within my system. The water goes out at one temperature, I want it going back to the boiler 20 degrees lower. All right, that's what I'm doing. So under design conditions, I've done my math, okay? I know the heat load under design conditions. I need 8 gallons a minute at 7 foot ahead. And let's say that is 100% dead on accurate. I install the delta T circulator. Under design conditions, it's going to sense those 2 water temperatures. It doesn't care what the water temperatures are. It doesn't fight with outdoor reset or anything like that. It only cares about the difference between what's going out and what's coming back, all right? In reality, what this circulator is going to do is it's pretty much going to size itself under design conditions. It's going to know, okay, I need 80,000 BTUs. I need 8 gallons a minute. At a flow rate of 8 gallons a minute, under design conditions, I will have a 20-degree delta T, and this is how fast I'm going. So it's going about not a little bit more than 50% speed under design conditions. Okay, we got 59 watts here, 9 watts here. That's probably going to be about, we'll call it 34 watts. All right. As zones close, I'm pulling fewer BTUs out of the water, right? That return water temperature is going to start to increase, and the sensor picks that up. And as the sensor picks that up, in order to maintain a 20-degree delta T, it's going to slow down, right? It's got to slow down. So it slows down to, another system curve, to meet another system curve. And another zone valve closes. Now the delta T is going to start to get smaller. The pump's going to slow down to keep it at 20. And that keeps going and going and going until I have my one single smallest zone calling. So let's say that one single smallest zone calling is right over here somewhere, okay? So under design conditions, that circulator is going to vary its speed between those two lines. And because I have 7 different system curves, basically what I have is a 7-speed circulator, and it's going to automatically switch those from one speed to the next as zones open and close under design conditions. But here's the thing. Every other condition as well, it's a 7-speed circulator. So instead of 0 degrees, it goes up to 5 degrees. I got 7 new speeds here, okay? It goes up to 10 degrees. I got 7 new speeds. As it gets warmer out, here's the other element of delta T that delta P does not do. As it gets warmer out, everything goes slower because my load is lower, all right? So the pump slows down as the load decreases. Now, at some point, here's 50% load. Again, 4 gallons a minute, 2 feet ahead. At 50% load, all zones calling, I'm at minimum speed. All right, I'm at minimum speed. And in fact, we're going to spend an awful lot of the heating season with this circulator working at 9 watts at its minimum speed. At that point, it's not a variable speed circulator. It's not going to change speed, and it's not going to maintain a 20-degree delta T anymore. But the point is, it's not going to be a 4-degree delta T. So we've kept that delta T as wide as possible for as much of the heating season as possible until we hit that minimum speed. Let me know, Rick, if there are any questions out there about that, about delta T and how it works.
None. They're just wanting to know, William has a question about, can we troubleshoot these types of pumps? Or do we just throw them away if something goes wrong? And I answered some of that, but for the most part, you can override these settings, to figure out if there's an issue. First thing we got to know, is there an issue with the pump or is it a system issue? And the pumps allow you to override and do some stuff for troubleshooting.
Right. I mean, the electronics are all solid state. I don't think we've seen an issue where the electronics have gone haywire on us at all, William. The only thing that could happen is, again, if magnetic crap gets into the system and causes the circulator to seize, might be the biggest issue. We have a bio barrier in our delta T pump to help keep some of that black iron oxide away from the magnets, which helps. And then at that point, anything beyond that would be a mag dirt separator for the delta T pump. Delta P pump has sure start, which helps alleviate some of that as well. But those are the more common situations. The electronics have been pretty bulletproof, I think. If that's I hope that answers your question in terms of what we're trying to accomplish with these circulators. But yeah, the black iron oxide magnetic stuff is more of a threat to these circulators than anything in the electronics. Is that right? Very good, very good, very good. All righty. As a zone, and now let's go back to this as a zone pump real quick. As a zone pump, 3 gallons a minute, 7 foot ahead, okay? Again, it's going to size itself. It's going to size itself, but this is the maximum speed it's going to go. And that, maybe that's 22 watts or thereabouts. That's the maximum speed, 3 gallons a minute at 7 foot ahead for that one zone. As it gets warmer out, again, that circulator is going to go slower. It's going to vary its speed basically based on how warm it is outside, because it's monitoring how many BTUs are being taken out. And if I got to keep that delta T at 20, I got to go slower, right? We're going to reach a point at 9 watts at some point where this is my minimum speed at 2 gallons a minute. So this is the variable speed range I'm buying when using it as a zone pump. Typically speaking, the smaller the zone, the less a VT2218 delta T pump makes sense, because it's simply not going to vary its speed very much. Really, this thing shines when we have a zone valve system, or at least larger zones, okay, larger zones, so we can maximize the variable speed range of that circulator. But again, as a zone pump, it's the only variable speed circulator that will vary its speed as a zone pump. So again, something to consider. Want to wrap up discussing the auto functions really quickly. Again, there is no such thing as magic. And that's one thing we still get questions about is there a button to push that it'll just delta P pump that'll automatically size itself? The only circulator that comes as close to being to automatically sizing itself is going to be a delta T pump. If you know the system delta T, you program it for that delta T, and again, it comes out of the box programmed at 20, but you can change it from 5 to 50. That's about as close as you're going to get to a self-sizing circulator in our industry today. That's really is about it. The auto functions, we have active adapt, there's auto adapt, other companies have auto, there's all these different things out there. They don't size they're not self-sizing functions. They have a specific purpose, and they do that specific purpose, they do that specific job very, very well, but it's not self-sizing if you think. Let's talk about how it really works, okay? Our active adapt is used in proportional pressure only, and that's all auto functions is for proportional pressure operation only, okay, proportional only. So what that means is it really is best suited for continuous circulation with thermostatic radiator valves. That's its best application. And every circulator that has an automatic function out there is going to work essentially the same. There's no real magic, there's no magic or secrets involved here. When it starts, it's going to work on a default curve. Our 0018, when we tie it in with the app, we will have 9 different curves that we could choose from, 9 different proportional curves that we can choose from. It's going to default to number 5. I'm sorry, 7 different curves, but it's going to default to number 5 right here, the second from the top. That's its default operating mode, and it's going to operate there to start. And what it's going to need some information before it decides to adapt to anything, okay? So at power up, it's defaulting to curve 5. The first time it comes on, it has to run for 90 minutes to kind of analyze the system and see what the heck's going on while running at curve number 5. And then another 30 minutes for system stabilization. And then what's going to happen is the algorithms are going to kick in. All right, the algorithms are going to kick in. And it's going to start figuring stuff out. But we're talking 2 hours of continuous operation here. All right, continuously running. What makes it change? Well, let's talk about thermostatic radiator valves for a minute, because they're modulating, right? They're opening and closing. This is what this is designed for, continuous circulation with TRVs at individual panel radiators. So when it's operating in normal functions, okay, we're operating on curve 5. As the TRVs are closing as a group, we're going to go slide down the curve. As the TRVs open, we're going to slide up the curve. So in order for this to change curves, when we're up here at a kind of a steady operating point, the system is going to need to see a 1.3 gallons per minute flow change for at least 20 minutes. And if we're in a steady state mode for stable loads, it needs to be about 60. Once it sees that, then it will jump either up 1 or down 1, depending upon the flow change. So let's say I'm operating way the heck up here. Okay, I'm operating way the heck up here on that line. And I've been there for a while, but now all of a sudden, maybe it gets colder out, who knows? The TRVs are wide open at this point, and that's a 1.3, I'm seeing a 1.3 gallons per minute flow change, and it has to happen for an hour. Once that happens, I'm going to jump up a curve and work up here and give me a little bit more flow, all right, to help deal with that change. On the other end, if I'm down here and the TRVs keep closing like it's getting warmer, I need to see a 1.3 GPM flow change for that 20 to 60 minutes before I jump down here and get a lower flow and lower headline performance curve. That's how they all work. They're all pretty much the same. They do essentially the same thing. Now, steady state operation, really what we're looking for is that, just bopping back and forth between these 2 lines. That's when active, adapt, and all the others are singing and dancing in the depth of winter, that's kind of what we're doing, just bopping back and forth between those two lines. It's not analyzing the system and saying, well, based on this, we must move over here. It's not doing that. It's just, we like to think, yeah, you press the button, it sizes itself. Not even close, not even close. And here's the other thing, it's gotta run, man, it's gotta run. If we are all of a sudden getting into an on-off operation, which is how we run circulators here in North America, all the zones are satisfied, they all close, we turn the boiler off, we turn the pump off, we start all over again, right? We either start all over again or we start off where we left off. There's no more adapting going on. When we stop flowing, we stop adapting and we start again, okay? The whole process starts all over again. So in a zone valve system, an on-off zone valve system, let's do that 8 gallons a minute at 7 foot ahead thing I have right here. So 8 gallons a minute and 7 foot ahead is where I want to be. In reality, it's going to work right there. Again, about 9 gallons a minute at 10 foot ahead. Not bad, not bad at all. Now my highest head zones, 3 gallons a minute at 7 foot ahead. That's where I want it to be. In reality, it's going to work there. Now check this out, because this is weird. This happens with any circulator, really. Has nothing to do with delta P, delta T, or active adapt or anything like that. It's a weird thing that can happen. Let's say my lowest head zone is 2 gallons a minute at 2 feet ahead. That's my smallest zone. If I were to plot that out on a system curve and see where it intersects, in fact, it would intersect right there. So my smallest zone, 2 gallons a minute at 2 feet ahead, the circulator would actually be going faster when that's the only zone calling, compared to my highest head zone being the only one calling, 3 gallons a minute at 7 foot ahead. It's weird. It's just how it works. You know, it's just how it works. It's an anomaly, but it does happen. But again, there's no adapting going on because we're not running long enough for it to do anything. The system's going to work. All right, the system's going to work. When zones open and close, you're going to see numbers changing, but it's not doing what we think it's doing. All right. Now, zone pump system, 3 gallons a minute, 7 foot ahead. That's where I'm working. It's going to work. Yep, it's going to work right there forever. That's just the way it's going to be. It's not going to change any, because it's never going to run long enough for it to change. It's just the way it is. All right, some key takeaways for today. Obviously, flow and head. It all starts with flow and head. We got to know the flow. In order to know the flow, we got to know the load, right? We got to do it. We got to have a good idea of the heat loss. But once we know the flow, we can actually get down to calculating the head loss and knowing what we're dealing with. All right. Then after that, it's system curves and pump curves. And there's the important thing. No matter what kind of a pump we use, system curve, pump curve, that's where it's going to work. Delta T is the exception to that rule, but everything else, the system will work where the system curve works, where the pump performance curve and system curve intersect. Has to. There is no such thing as magic. There is no such thing as magic, just illusion. Things only change when we change them, but you have to do it skillfully in secret. Then it seems like magic. I like that. I found that this morning. I like that. I thought I'd share that with you. And programming matters. All right, programming matters. We need to know the capabilities of the circulator so we can match them to the job as best we can. All right, a lot of folks will tell you, hey, looks like delta T is just simply the way to go. It's going to figure it out for itself. And that's an absolutely accurate statement. The one caveat is when using zone pumps. All right, yeah, if it's a small zone, we're going to get a little bit of variable speed in this, but not much, and it's a very expensive circulator for not much variable speed in this. So your performance advantage might not be that big over, say, a delta P circulator programmed properly. And in some cases, if you got a really small zone, you might be better with a 0018E where you can actually set a fixed speed. So, and again, that's something we'll discuss in future sessions. And lastly, don't ever forget, rust never sleeps. Rust never sleeps. All righty. Well, thank you, folks. Time for more questions. How are we doing out there in question land there, Rick?
Looks like we're caught up, at least with what I'm looking at anyway. William had one of the last questions, and I think we're up to that point anyway.
All right, terrific. And it wouldn't be a webinar without the dogs barking.
Yeah.
All right, so folks, let's hear some more of your questions. I just like to, does anything here make sense to you? Anything here new? Anything here sound crazy? Let's hear what you have to say, because this is the important part of the session. I mean, we want to make sure that you folks out there have gotten what you wanted out of this session. So Robert said, Robert, that was good. Matthew was good. Again, ask away. Pretty much anything and everything is on the table. I don't know what they're barking at, but something is really annoying those dogs right now.
They're hungry. You have to go feed them.
Those dogs are always hungry, and they get more treats than any other animal I've ever seen. My goal in life is to, you know how they say if you lead a good life, when you die, you're reincarnated as a higher being. My goal is to lead as good of a life as I possibly can, so that when I die, I come back as my wife's dog. That's a higher existence. Well, alrighty, I guess we got everything covered. Any more questions out there, folks? Please type them in now. Otherwise, we can say thank you for a great session. We really appreciate your input and your time. And again, last call for questions. Let's see what you got.
I think you got it. We got people signing up.
All righty, folks. Well, hey, thank you again. Appreciate it. Rick, always a pleasure. I hope you feel better soon.
Hey, thank you.
All righty, and thank you, Laura. Thank you, everybody out there. We really appreciate the gift of your time today, and just make sure you take care of the people you care about, and don't forget to hug the right people, just as you never know.
Right.
If you hug the right people today, you never know. So thank you all. Have a great rest of the day and great rest of the week. Take care.
Thanks, John.
Bye-bye.
Bye.